Okay, so picking up where we left off, I think we had just discussed, let's see here, this line here, that for all n in the integers, 3n is less than or equal to 5n. We concluded that's false, and an example would be if n is any negative number, like n equals -1, that will give you that 3 times -1 is actually greater than 3 times -5. Okay. Oops. 5 times -1. Talking and writing at the same time is tough. Okay. Let me clear that now. If I remember how to do this on Zoom. It's been a while since I've had to do Zoom. Where's my toolbar? There it is. I see it now. Okay. Let's just erase all that or clear it. Perfect. Okay. Now, let's go over here, grab that. Looks good to me. All right, let's look at the next one, number 6. For all x and for all y, x cubed equals y cubed implies that x equals y. And I'm going to say that that is true. And the reason is that we can get from the statement x cubed equals y cubed. We can take from that statement and force that x equals y by multiplying both sides of the equation by 1/3. Hopefully it's not too messy, just using the mouse as my cursor here. My daughter stole my iPad today. Okay, so if I apply 1/3 to both sides, right, I get that x equals y. Okay, so the first statement, if x cubed equals y cubed, if that's true, then I can force it to be that x equals y. So number 6 is true. And now let me clear all my drawings. Now let's look at x equals 7. Or sorry, let's look at problem number 7. It says for all x and for all y integers, if x squared equals y squared, then x equals y. And I claim that this is false, and here's why. I could take a counterexample would be x equals 1 and y equals -1. Okay. So it is true that x squared equals y squared, right? 1 squared equals -1 squared. That's true. Okay, this ends up being true, but it's turns out that x equals y ends up being false, right? So x equals y is false. So x does not equal y. Okay, so that's why this statement can be concluded as false, as there exist examples of x and y such that their squares are equal, but their values are not. This is a counterexample right here. And you might be like, well, wait, what the heck? Why can't I just take the square root of both sides? But it doesn't work because the square root, applying the square root of both sides of that thing is not an invertible function, right? X to the 1/3 is an invertible function. X to the 1/2 is only invertible above the y-axis, right? So, in other words, if I took x squared plus y squared, I don't know if that makes sense. X squared plus y squared equals 5. Or maybe I should do 25 or something, right? That's not a function because two different inputs, in fact, sorry, one input could have two different outputs, right? This x value has two different outputs in this curve. So what we do is we restrict our attention to the top half, right? So we restrict the function. And so what's going on here is this counterexample is I'm finding a positive value x and a negative value of x and negative value for y. And showing that it is possible for x squared to equal y squared, but for x not to equal y. Okay, hopefully that makes some sense. If not, just ask me about it again after class. Let's clear that. Let's scroll down now. Yeah, let's turn off annotations to scroll. Okay. Combining quantifiers. Express the following statements using a combination of qualifiers. So for every positive integer, there exists a larger integer. Okay, so for every x in the positive integers, there exists a y in the positive integers such that y is greater than x. Okay, this is just translating, so hopefully it's clear. For every positive integer, that's this piece right here, there exists another positive integer that's larger. Okay. See, 2, there exists a smallest natural number. There exists an n such that for all y and n, y is greater than or equal to x. Okay. I think that number is 0, in fact, right? But yeah, that's the statement. For every real number, there exists another real number that is greater. Okay, so for all x in the reals, there exists a y in the reals such that y is greater than x. Hopefully those translation statements are not too hard. Okay, determine the truth value of each of these statements if the domain consists of all integers. So for all n and n plus 1 is greater than n. I'm going to say that one's true. I think I did an example like that earlier. Now let's see here. There exists an n in the natural number or in the integers such that n cubed equals -1. That's true, and hopefully you see what the example is. It shows that's true. Let's see. If I take n equals -1, then in fact n cubed equals -1, because that's just -1 times -1 times -1. So that's -1 times -1 is 1, so I get 1 times -1. Check. Okay, now there exists an integer n such that 2n equals 5n. That is true. I think there's exactly one example where that happens, and can you guys guess what it is? N equals 0. You get 2 times 0 equals 5 times 0. Okay. For all n in the integers, 3n is less than or equal to 5n. Again, I think an example where this is false would be if you take n to be negative. Okay, take any n less than 0, and you'll get that 3n is actually bigger than 4n. Okay, so that's your counterexample there. Okay, next one. For x and for all y, x squared equals y squared implies that x equals y. Well, we just did that on the previous page, right? This is kind of a duplicate there. But again, the reason is if you take x equals, let's say, 2 and y equals -2, then you get that x squared equals y squared, but it's not true that x equals y. Okay, scroll down again. Determine the truth value of each of the following statements if the domain consists of all real numbers this time. Okay, so there exists an x such that x squared equals 2. In this case, it's true. X would have to be the square root of 2, and that is a real number. It's not a rational number, it's not an integer, but it is a real number. So that value right there will work. Also, I guess you could take x could be either positive square root of 2 or it could be negative square root of 2. Okay, there exists an x such that x squared equals -1. This one's false because the solution here is actually x equals the square root of -1, and that's not a real number. It is a complex number. We typically call it I, or the imaginary number, right? So it would be true if I went to the complex numbers, but it's not true inside the real numbers. Next one up. For all x, all real numbers x squared plus 2 is greater than or equal to 1. That might be easier if I translate that into for all x squared is what? Greater than or equal to negative. I just subtract 2 from both sides, I get -1. And so it is true, x squared is always greater than or equal to 0, so it's definitely bigger than x squared. Sorry, greater than or equal to -1. So that one is good. That's true. Okay, next one. For all x in the real numbers, 2x is greater than 2. Yeah, why would that be true? No, that's false, right? It says wrong. Don't even know why I'm looking at this. That's clearly false because I could take x to be -1, right? So to disprove a for all you gotta do is show that there exists, right? There exists an x such that 2x is not greater than 2. In this case, if I take x equals 1, sorry, x equals -1, then I get 2 times -1 is not greater than 2, or I could just say is less than 2. Less than or equal to 2 is how you negate a greater than. Okay, so that right there, x equals -1 is my counterexample. Next one up. For all x, x plus 4 squared equals x squared plus 16. Yeah, that's like the well, that's like the, I don't know, high school algebra fallacy, right? That you just square the x and you square the 4, right? But really, if we're going to FOIL this, we need to do the following, right? X plus 4 times x plus 4. And so I should get x squared and then 2 copies of a 4x, so that should be 8x plus 16. And that is never going to equal x squared plus 16. Unless x is 0, I guess, right? I need 8x to be 0. And so that would force x squared to be 0. That would force x to be 0. So that's false because there exist integers x for which this isn't true. In fact, it's false unless x equals 0, right? So whenever x is not 0, this is false. Okay, last exercise. Translate these statements into English. Let S of x be the statement x is slow, and T of x is the statement x is a turtle. And then our domain is the set of all animals, the domain of a discourse. So now we're going to say for all x in the set of animals, being a turtle implies that you are slow. Okay, and so one way of writing that would be to say that all turtles are slow. Okay, being a turtle for all x, being a turtle forces you to be slow. The next one is for all x, s of x and t of x. So that is for every x, everyone is a slow turtle. Well, I guess every animal is a slow turtle would be the way that you would write that. So I might say every animal. And we can call every one animals, but every animal is a slow turtle. So you're both slow and you're a turtle. Now the next one is there exists a slow animal that implies turtle, right? So wait, some slow animal, right, is a turtle. Yes, there exists a animal that is slow and it is a turtle. I think that's the way you want to look at it. Maybe it's easier to look at it via implication. The statement S of x implies T of x is logically equivalent. Maybe I'll do an if and only if statement. S of x implies T of x is equivalent to the statement that, what is it? T of x, or isn't it not S of x? Maybe that's supposed to be some slash. Okay, there exists some, well, no, there exists an x such that being slow implies you're a turtle. Think about this one. This might be something to think about there. There exists an x such that being slow implies that you are a turtle. There exists an x that is a turtle and it's not slow. Okay, next one. Clear all those. Last one. There exists an X such that, so there exists an X in the set of animals that is a turtle and it's not slow. So that means there exists a fast turtle. Hopefully that one's clearer than the number 3. Okay, so that's it for today. Go ahead and fill those out and submit them, and I will see you all on Friday. Have a great day.